Suppose there's a plane in 3D, in space, of course, the plane, and we know two things about the plane. We know a vector which is normal to the plane, and I will call this vector n, and we also know the components of n. That will be n1, n2, and n3. Now, suppose we also know a point where the plane passes through, and I will call it A, and say the coordinates of A be x1, y1, and z1. Now, before I go on, what you can think about this situation is that suppose you have your eye is here, okay, and look into this direction, this eye here, and you will see something kind to this. See, the plane will look something like this, right? And the normal, the vector which is normal to the plane will be something like this. This is n, and you see it's perpendicular here, so that's what you will see. And of course, the point A would probably somewhere here on the plane, or inside the plane. So the next thing we would do is by assume that suppose that the point P, which is allowed to freely move anywhere in the plane, and because we do not know its coordinates, we call that the point P x, y, z. By forming the vector AP, that would be x minus x1, y minus y1, and z minus z1. You should actually realize this. If you look at use this diagram here, this illustration here, the P is somewhere here. This is A and P. If you form the vector AP, you realize that the vector AP and the normal, they are perpendicular to each other. In other words, this implies that AP, when you calculate the dot of AP and n, will be equal to 0. And so this is how actually you use the concept of dot product to two perpendicular vectors to find the equations of planes. Now I'm going to look at one example on finding equations of plane. Here we see that the normal vector is 2, negative 1, 3, and this point is the point A in the formula, and the plane passes through this point. So let's write down that n be 2, negative 1, 3, and A is we let A be negative 1, 2, 4, and we assume that there is a point P, although it's not given here, but we suppose that's the case, and let it be x, y, z, the coordinates. And so what we're going to do is first we're going to form AP, and clearly this is x plus 1, y minus 2, and z minus 4. And to find equations of the plane that we're investigating right here will be equivalent to finding the dot product of AP and n, and that will be 0. So if you perform the dot product, the AP and the n, the outcome will be this. You will have 2 from the vector n, x plus 1, and then you have plus negative 1 times y minus 2, and also you have plus 3 times z minus 4, and all this is equivalent to 0. And once you simplify this, collecting the constant term and so on, you then get these equations, and this is the equations of the plane in the problem we just tackled. At this point, you probably realize something very profound. In a way, look at this vector n, the components 2, -1, 3. Look at these equations. What do you see? Now you probably notice that the coefficients of x, y, and z, they are 2, -1, and 3. Right? 2, -1, and 3. So the coefficients of, or should I say, if you know the normal to a plane, you would able to form this part of the equation of that plane, because you know the coefficients would be the components, the corresponding components of the normal vector to the plane. And also, if you think about this value 8 is in fact the dot product of vector n and also the vector position vector of A. So you can try this. If you dot n and the position vector of A, you end up getting 8. Okay, so next we're going to look at another example on how this can be useful to determine some important information. So for this particular equations of planes here, you can deduce a few things. First, we know that one of the normal vectors, there are many normal vectors, you see, because like in a plane, you might have a normal like this, you can call this n. You might even a normal which is longer somewhere else, you can call this n1. So there are many normal vectors to that plane. Anyway, one of the normal to the plane would be, just write down the coefficients of x, y, and z is -1, the coefficient of z. So 2, 3, -1, and they form the normal vector. And another useful concept or approach or method is to find a point on the plane that the point lies on the plane. So very simple. You just need to find values of x, y, z so that it satisfies and eventually it sums up to the value 8 here. So I could assume that I have the value x equals to 1 and then y equals to 1, or maybe I let x equals to 2 better. So then I will have 2 substituting x with 2 plus 3 plus 1, and then minus z. What would z be to get 8? Well, of course, this should be -1 to get 8. So all the points which lie on the plane is this point 2, 1, and -1.